approach, right? So here's a recursive dependent contract over trees, where we can see the leaf node will always be checked to see if it's null. We will recur on the left subtree with some bounds, which are passed in here, to indicate that the values to the left in this tree need to be between the value at this node and the low, which starts at negative infinity. We check that the predicate is between our bounds, and we check that the right-hand side is larger than the value at the current node. This will ensure that this tree is a binary search tree. Incidentally, checking this contract means that we have to traverse the entire tree, which takes a complexity from order login for a binary lookup to, if we check this contract before we do it, order in. So that's not great. It turns out that there are a lot of ways that contracts can change the results of the program by just monitoring them, from asymptotics to where errors might occur to any number of other things. Moreover, the choice of the contract system and the evaluation semantics you choose for that contract affect how those contracts will change your program. And these behavioral differences are known as monitoring strategies. They're strategies for contract enforcement. So the very first one that we typically see is Findler and Felicen's work in 2002, where if we check that 5 is a nat, we get 5, -1 produces an error. Checking that a pair is a nat does the same thing that we just saw before. There was some work later in 2006 by Hines et al., where they started delaying parts of the program that you never looked. Right? So here, we take the first element of this pair, it's 5, and we never use the -1 in our program, so we never produce the error, because we never actually check that subcontract. There's been even further work by Demolas et al. In 2009, where every time we go to enforce a contract, we hand it off to a worker thread, and that worker thread will check the contract concurrently and synchronize with the user program during I/O events, only reporting errors if it's found them by then. It turns out there are a lot of monitoring strategies. These are the 8 most common in the literature, from eager monitoring to semi-eager monitoring to that master worker style by Demolas et al. To finally synchronous, asynchronous checking. For the rest of the talk, I'm just going to focus on these first 4. They're a little simpler in terms of semantics, and they'll be a lot easier to reason about through my examples, but we do cover all 8 of them in the paper. Right. So the problem with these strategies really is that sometimes you really do want to check that a tree is a binary search tree. And sometimes you only want to check the parts you look at. And none of these is a perfect fit in every situation. We always want something, and we sometimes just can't have it in a fixed strategy semantic, in a fixed monitoring strategy world. So we think that the contract writer should make this choice. Like that. If I say that I want this checked eagerly, it should get checked eagerly. If I want this checked semi-eagerly, I should get back some sort of promise that I can force that'll check the contract. To check it with a future contract, I should start a concurrent thread and synchronize with it later and get a promise back. To check asynchronously, I should just spawn a thread and try to do some best effort, where if at the end of it, the contract's done running and it produced an error, I should find out. And if it never finished, well, it did its best effort, right? More importantly, because we're calling check recursively in these pair contracts, we can recursively determine which strategy we should use at every single enforcement site. So this is a pair contract for 2 eager subcontracts. We check that eagerly, and we get the same results that we saw with the original examples. But if we just change this to a future contract, we get back a promise that it'll eagerly check that it's a pair of natural numbers. And it's only when we force that pair that we get the error. We can also do this the other way. We can put 2 future contracts around those 2 subcontracts, use eager at the top, and get back a pair of promises. If we force the second one, we get an error because that's not a natural number. And here's back to that binary search tree I was talking about, right? And now instead of walking over the entire tree, we can specify which strategy to use for these recursions. And we can even pass it in as a parameter. So here, if we use eager, we'll just do the order and traversal I described. With future, we'll do the order and traversal in parallel and only get the results at the synchronization points and only wait on those that we need. With asynchronous, we'll just start this operation concurrently, and if it finishes, it finishes, and if it doesn't, the program seemed to go okay anyway. And finally, with semi-eager, we'll only get the nodes that we force. So the thing is that each of these monitoring strategies subverts the evaluator, right? It's doing something that changes how the program works by putting a contract on it. And if we want to be able to change these in and out, we have to sort of play this game of subversion in a more formalized, abstract way. So basically what's really going on is we have this user evaluator that has contracts and values flowing into a contract evaluator, and we have results and errors flowing back out. So for an example, let's look at eager monitoring. We have this user evaluator that asks that 5 is a nat. We build a contract evaluator that does the check, and then we synchronize with it, getting the result back. For asynchronous monitoring, we just get rid of that synchronization point. It might produce an error, or it might not get there before this program finishes. For future monitoring, we add the synchronization point when the user forces the thunk we give them. And finally, for semi-eager monitoring, we hand back a delayed reference to that check that they wanted, and they're allowed to force it whenever they'd like. In the absence of side effects, I should note that semi-eager and future monitoring look the same. They're doing different things in terms of when the computation starts, but they always just report the error at the synchronization point. So how do we get all of this in our language? Well, it turns out we don't need a lot. We need to be able to spawn processes. We need to be able to make channels, read and write across them. We need delay and force so that we can slow down some of this contract checking. And we need to be able to raise and catch errors to propagate them across processes. We also need macros for check and call by value. That's only because we don't want to evaluate some terms beforehand. In a lazier language, this shouldn't be a problem at all. All right, so with these tools, how does this look? For the purpose of this talk, I'm going to align spawning processes and creating channels and also propagating errors. It's all in the paper, but the semantics can get a little intense. Right, so this is a vanilla contract checker. We have some contract value, which is the evaluated contract we want to check on some expression E, with positive and negative blame labels. So we evaluate E, and we ask if it passes the contract. If it does, we return it, and if it doesn't, we blow up. So all we have to do to add eager monitoring is abstract this out into two processes, where the user processor reads the result of the contract, and the contract process simply writes the result of the contract. And that's all we have to do to make this change. And then for future monitoring, we just delay the read. For semi-eager monitoring, the only change is moving this delay down to the contract check. And finally, for asynchronous monitoring, we just hand the user process E. We start the contract process concurrently, and if it gets to blame, it gets to blame, and if it doesn't, we can just keep going. This is how we get that best effort behavior I've been describing. So in summary, these are what those 4 strategies look like when they're rewritten using this style. We just add these delays and move them around to get this very precise behavior, and it was by separating these 2 evaluators that we got here. Moreover, we've seen that these directly interoperate with one another. Right? None of these is a best fit in every situation for every single contract system, but it's nice to be able to just say, well, I really do want that tree eagerly evaluated or semi-eagerly evaluated. Or more importantly, I actually want you to check the value at this node when you get to this node, or only when I ask for the actual value to be extracted. These communication facilities that we've built here, though, and introduced to the language give us even more power. So if you'll consider for a moment what it would look like to have a full tree, and we want to know if a tree is full, right? And so the way you check a tree, if a tree is full, is you ask if both of its subtrees have equal heights. And the way that you ask if those trees are full is if you ask if their subtrees have equal heights, down to the leaves. The problem, though, is at each level, you have to propagate the heights back up. So to write a contract to ask if a tree is full requires a traversal of the tree necessarily. There's no way to really delay it. It turns out that if you lazily evaluate the nodes, and at each one you start a sidechain communication that's waiting on children with new channels that it hands down to the recursive contracts, we can propagate these heights back up, only listening and waiting for the ones that we've actually seen during our traversal. And this will actually let us do that login lookup through the tree, checking the parts of it that we've seen are full, and not touching or trying to check any of the others, while still ensuring that the parts we've seen are in fact under that invariant. Some of the other results we have in the paper are full semantic descriptions of eager, semi-eager, asynchronous, and future contracts, proof sketch of type soundness, and an embedding of the Findler-Felissen 2002 work into our eager monitoring semantics, and implementation sketches of lazy, temporal, that master-slave, master-servant style, and finally synchronous contracts, which are like asynchronous contracts except that each one registers with a centralized manager, and at the end we can just ask the manager if it's actually checked everything that it knew that was going to be checked. We also have a full implementation. You can see it on GitHub. It's currently a prototype, but it works. And in some of the timing results we've done for the fullness checking, we eventually get over the cost of the thread overhead versus the racket contract system, which has to traverse the tree to check fullness. Thank you.
Questions?
So supposedly that you have this nested checking of the contract for the BST tree. Mm-hmm. Did you evaluate the cost of all the sparks that you initiate?
Yes. So that's what I was saying earlier about the fullness checking. It turns out that by just slowing down the checking and not exploring the whole tree, for small samples, of course, the built-in chaperone system and like the racket runtime is going to be faster. It really is over these processes. However, with larger data structures, if you want to check invariants, but only on the parts you see, then you're necessarily going to win, right? And it's not even a matter of thread overhead at that point. It's when does the thread overhead stop being lower than the cost of traversing a structure?
What do you mean by type soundness here? The language type?
Yes. We have a fairly weak type system, so we don't actually type processes. We just assume that we enforce that they're well typed, and we have a actually typed lambda calculus under that we prove type downless for.
Let's thank Cameron.